Hello guys, welcome to Coding. In this video, we are going to see the Leetcode problem number 222, count complete tree nodes. Let's get into the problem. So the problem statement is, you are given a root of a complete binary tree, return the number of nodes in the tree. According to Wikipedia, every level except possibly the last is completely filled in a complete binary tree and all nodes in the last level are far as left as possible. It can have between 1 and 2 power h nodes inclusive at the last level h. This is an algorithm that runs less than big of n time complexity. So yeah, let's define the problem. So the first step to solve any problem is to define the problem clearly. So you'll be given a root of a binary tree. It's a complete binary tree. So this is the input and output should be the number of nodes in the tree. So before moving on to approach, we need to know what is the term complete binary tree means. Complete binary tree means, before that, what is binary tree? Binary tree is nothing but a tree which consists of nodes, and nodes will have maximum of two child, maximum of two child, max of nodes child, count of nodes. Let's say count of nodes child is 2. So maximum a child can have two children. So it can have zero child, it can have no child or one child or two child. So this is the possibility for any node in the binary tree. So let's see what is complete binary tree. Complete binary tree is nothing but a binary tree which consists of nodes, but except the last level the nodes are completely filled. So when we take a binary tree, let's say this is the binary tree. So this is the first level, the second level, the third level. So first level is having one node, second level having two nodes, and third level having four nodes. So this is the completely binary tree. So let's consider other question. So the definition of complete binary tree is nothing but all levels in tree are filled. So this means the trees are filled is nothing but every node has two children. This is the meaning for fill. So all the levels in the tree are completely filled, and final level, that is the last level, may or may not be filled. May or may not be filled. So this is the definition of complete binary tree. But and the when the tree is filled, there is no problem. So if the tree is not filled, it should be in order of left to right. So let's see what does this mean. So let's consider a binary tree. So we'll consider this first. This is first case. That is yeah, first case. This is second. and just wait. So and for each trees we are going to find whether the tree is a complete binary tree or not. So will we consider this tree? So for each node, so we'll name the levels: first level, second level, and the third level. So you can see that the first level nodes are filled and second level nodes are filled, and we consider third level, that is last level, the nodes are not filled. So every nodes are present. Every node of previous level, sorry I have mentioned wrong. So every node of previous level has two child. So this is the meaning for field, and the root has a single child. So sorry, root is a does not have a parent, so we'll consider the first root alone as completely filled. So the definition of complete binary is nothing but all levels in the tree are filled, and last level may or may not be filled. If the tree is not filled, the nodes are ordered from left to right in the last level. So this is the 11 this is the definition. And what is mean by fill? Fill is nothing but every node of previous level has two children. So yeah, we'll consider the first level. So we'll check whether the previous level has two children or not. So in this case of first level, we consider this as true. So the first level only has one node. So we'll continue. So in second level, we'll check the whether previous nodes have two children or not. So previous 11 nodes are only one node, which is root. So root has two child. So it is complete. The level is completely filled. So we'll move on to third level. So in third level, we'll check the previous level nodes. So there are two previous level nodes, that is 1 and 2. So we'll check for the 1. So 1 has two child. So this is completely filled, and we'll go to next node. So in this node, it clearly see that there is no child. So this is considered to be not filled. So this area is not filled. So and we can clearly see that the last level nodes are ordered from left to right. So last level nodes are filled from left to right. So we consider this as complete binary tree. So now we'll move on to next tree. So in this tree, the first level has only one node. So the root node is considered to be uh, completely filled. So we'll move on to next level. So in the next level, we need to go through the previous level nodes. So previous level node has two child. So this level is completely filled. Now we'll move on to third level. So third level, we'll check for the previous level nodes. So previous level nodes are these two. So you can clearly see that the first node of previous level does not have two children. It has only one child, which is to the right. So you can say that the last level is not filled. So now if the last level is not filled, we'll check whether the nodes are filled from left to right or not. So you can clearly see that there is no node in the left of the previous nodes left. So there is a node to be come before this node which is not present. So we'll consider this as a binary tree only. So it's not a complete binary tree. So now we'll move on to third test case. So in this case, we'll consider the first level as completely filled and second level as completely filled because the previous level node is root, so it has two child. So we'll continue. We'll now go to third level. In third level, we'll check the previous level nodes. So previous level nodes does not have two child. So here is no child and here is no child. After this, we can really see that last level is not filled. So we'll now check whether the nodes are arranged from left to right or not. So there is no nodes in between the end nodes. So we'll consider this as non-complete binary tree. So this is only a binary tree and not a complete binary tree. So this is all about the complete binary tree. So yeah, What are the values present? So we need to find the corner case. So corner case is what happens if the root is null. So this is the corner case, and what are the other corner cases? So what are the values present in the nodes? Values in nodes. So we'll check for the corner cases. So they have said that the number of nodes is 0. So there is possibility of null nodes. So if the root is null, what we need to return? So we will return 0. So there will be no nodes, right? And what are the values in nodes? So what are the values in nodes? Node has value of range 0 to 520 by 4. So but they have mentioned that the tree is guaranteed to be complete. So there won't be any invalid cases. So this won't be present here. So only the valid complete binary tree are present in the input. So how are we going to find this number of nodes? So that's all about the problem definition. Now let's move on to approach. So second step is approach. So how can we approach this problem? So first approach that comes to everyone's mind is to go traverse over each node and keep track of the count variable. So count, so traverse each node using any of the methods, traversal method like in order or pre-order or post order, and keep on incrementing count if non-null node is present. So finally we return the count. So this is the first approach, and the time complexity of the approach is go of n, and the space complexity that it takes is, so in recursion the call stack may go up to size of height of the tree. So we go of tree height. So this is all about the space and time complexities. So now let's check if there is any other approaches available that is very efficient than this current approach. So, so can we use the property of complete binary tree? So complete binary tree has nodes, complete nodes, right? So we'll check for each node. We'll check whether the left and right are having at present at each, I mean the same level or not. So if the left and right nodes are present at the same level, we can find the number of nodes using a formula. So what is that formula? It's nothing but number of nodes n equal to 2 into, so when you can consider the first level there is 1, second level there is 2, third level there is 4. So we can clearly say that there is the number of nodes is equal to 2 power, so the total will be 7, right? 2 power level minus 1. So in this case, the level is 1, 2. So levels are especially as 1, 2, 3. So 8 minus 1, which is 7. So this is the formula to find out the number of nodes of a perfect binary tree. So let's see what is perfect binary tree. So every internal node has exactly 2 child, and if nodes are at same level. This is the definition of perfect binary tree. So if a tree is perfect binary tree, the number of nodes is nothing but 2 to the power last level minus 1. So this is the formula. So how can you apply this formula? So what we are going to do is we'll for each node we are going to check the whether the nodes are I mean the left and right nodes are at same level or not. So if the left and leftmost and rightmost nodes are at same level, it is the case. So what will we do is nothing but return the level from top to bottom minus 1. So or else what we'll do? So consider this case. So what we'll need to do? So in this case, what we do is we'll just add up the what to say? We just add up the number of nodes in right to the right. So when you are present at the node, we'll check the number of nodes in the right. So the number of nodes in right is nothing but 2 to the power the maximum, that is the least level. So in the left and right, the depth is nothing but left has depth of 4 and right has depth of 3. So we can have formula of 2 to the power 3 minus 1 by 2. So what happens is we are considering this as a tree. So why we are considering this? So because we are choosing the least level of current nodes leftmost and rightmost. So in this case, you can see that left has value as 3 and right has depth as 4. So we are choosing least. So in this list, so what we are trying to do is we'll just add the, so what will be the count of nodes in this selected nodes. So it will be 2 to the power 3 minus 1. 2 to the power 3 minus 1, right? So we are ignoring, we are going to include only these nodes. So how can we include only these nodes? So what we do is we'll find the answer. So it will be 7. We'll divide it by 2, which will lead us to 3, and add it by 1. So what we can do is we can just ignore this. So 2 to the power 11 by 2 will give us the result of these nodes alone. So finally, after finding this, we'll go to the left node. So again, we'll apply the same formula recursively. So finally, we'll be able to get the answer. So 2 to the power 3 is 8 by 2 will be 4. So abstractly, our steps for our approach is nothing but find the for each node, traverse each node. First step is traverse nodes. Find left and right depth. So if both levels are equal, that is if L left depth is equal to right depth, what will return is 2 to the power L minus 1. Or else what we'll do is we'll return the number of nodes in least level, that is 2 to the power least of min of L comma R, plus if the minimum is left node, what we'll do is return find count of, let's say find C of, if the min value is right, we'll pass left node, or else we'll pass right node. So this is the formula we are going to use. So how can we use this steps in our approach? So let's get on to coding section. So when we come to a node, we'll check if the node is null or not. If the node is null, we'll return 0, or else we'll find the height. Left depth, will say depth is equal to depth of root dot left. Right depth is nothing but depth of root dot right. So after finding depth, if left depth is equal to right depth, we'll return math dot power of 2 comma left depth minus 1. So or else what we do is, if left depth is less than right depth, we'll return math dot power of 2 comma left depth by 2 plus count nodes of row dot right. So or else we'll return and dot power of 2 comma right depth by 2 plus count nodes of row dot left. So how can we find the depth of f a node? So we get the node. So left depth can be calculated by using, so we'll have a helper function left depth and also right depth. So left depth is nothing but, so let's have initially our depth as 0. So while node not equal to null, we'll increment the depth and move node to left. Finally we return the depth. So this is the same formula, the same step for finding right depth. Right depth is nothing but to move to right. So let's take this. So what happened here? So possible from double to int. So we'll convert this to int. Let's take this up. So we'll add it here too. So we got a wrong answer. So what is the problem here? So we have left depth and right depth, right? So if left depth is greater than right depth, so we'll change this condition. Why we are changing this? Because if the left depth has greater change, so let's check this. So what we can do is, if left depth equal to right depth, we'll return this answer, or else what we can do is we'll return 1 plus count nodes of root dot left plus count nodes of root dot right. So actually I have made mistake in the previous step. So I have told that when the for each node when we check with the depth, if the left has 4 and right has depth has 3, so we'll just add this and return, add this and go to left, but this doesn't work for many test cases. So what we can do is, when we find the imbalance in depth, we just add current node and return the node number of node count of left and right. So yeah, we'll check this up. So we need to pass the roots. Working fine. Let's check for the test case. It's working fine. Let's submit it up. Yeah, accepted. And as I previously discussed, so the time complexity of the approaches, we go off what to say. So what will be the time complexity of the approach? So for each node, it will check for left and right. So it will go off n. But in terms of time complexity, it is not less. I mean, not exactly big of n. Since for some cases, some many test cases, it will be decreased to n log n. Since when we reach this condition, so when we reach this condition, we don't go further checking up. So we will just return the number of nodes, right? Otherwise, we'll go to each nodes. So yeah, actually I'm not sure about the time complexity, so I'll discuss and update in the description. And the space complexity is of um, log n. So it's because when we find the depth of a node, we'll go from top to bottom. So it will be the height of tree. So this will be the space complexity. The stack space will go up to the size of that is the height of the tree. So approach for this problem is recursion. So yeah guys, that's all about this problem. So thanks for watching this video. Have a great day.